Okay, here we go. We're gonna do something today that the first time you see it, you might not like it right away, but by the end of today, you'll get it without a doubt. But we want to do what's called implicit differentiation. What we've done so far is explicit differentiation. So, for example, we've had equations like y equals 2x plus 1, y equals a sine of 4x, or y is equal to x to the third minus pi x plus 2. Now, these are examples of explicit equations. And what that means is that they are explicitly solved for one variable. So they are solved for y. And once we're given y, we can then find the derivative pretty easily. And we often do that, especially with functions. You put in a value for x and you get an output of y. But implicit equations, well, that's different. Say, for example, x plus y is equal to 2. Now, that's not explicitly solved for y. Could you solve for y? Yeah, it's no big deal. It still makes a line. But if we have something that looks like this, x squared plus y to the third is equal to 8, well, that's a little bit different, isn't it? Or if we had something like x plus xy is equal to the sine of xy. Goodness, how to, is that you? Or is that you? Can you do it again? Okay, well, all right, all right. We'll try to be really boring so she'll yawn again, and she'll do it. Okay, do you notice how this would be really difficult to solve for y? But yet it still has a rate of change. It might not be a function. You see, we've always looked at finding derivatives of functions that look like that. But what about equations that look like, say, that? I mean, the fact is that has a rate of change at different spots. I don't know what that equation is, but there is an equation that will model that. It doesn't, so it's not a function, but we can find the rate of change. And so we need to come up with some new terminology. This is the derivative of the function with respect to x. This is the derivative with respect to x. This is the derivative of y with respect to x. See how they are all with respect to x? But this one names the function f, and this one names the function y, or names the variable y. This one does not. And we are going to use this terminology to find a derivative of x squared plus y squared equals 36. We're going to do what's called implicit differentiation. And I'll write it out lengthy the first time, but then after that, you'll just know how to do it. So do you know what the graph of x squared plus y squared equals 36? Do you know what that looks like? Circle with a radius of 6. Very good. So you agree it does not pass the vertical line test. And so, we don't really just want to solve for y. We want to find the derivative in a different way. So I'm going to take the derivative with respect to x of all of the parts. Now, when you take the derivative, what happens to the power? It reduces, and it's almost as though this d over dx absorbs that power. You know what I mean? So I'm going to write it in a way that's unique to you, and we'll never do it again, but this will help you understand why implicit differentiation works. What is the derivative of x? All right, what is the derivative of x squared? 2x. Now, notice how the power was reduced by 1, correct? I'm going to absorb that x with the d on top here, okay? You might say why. Ask why after you see it all, okay? Plus, what's the derivative of y squared? 2y. And one of those y's, the y that was reduced, will be absorbed in the numerator. And what's the derivative of 36? 0. And anything times 0 is 0. Well, look at what you have. What is dx over dx? That's 1. So you're just left with 2x plus and derivative of y with respect to x. Another way of writing derivative of y with respect to x, we've been writing it all along, is y prime. That's what derivative of y with respect to x is. Times 2y is equal to 0. Now, what we're used to solving in this class would be solving for y prime. How would you solve for y prime? We just did find the derivative. We subtract 2x, y prime times 2y is equal to negative 2x. We divide by 2y. We get y prime is equal to negative x over y. So we'll talk about what we did, but first let's make sense of that. It says that the derivative is negative x over y. So that's different because we now have a y in our equation, don't we? Well, you guys told me that this graph makes what shape? With a radius of 6. So as I sketch this graph right here, look at this coordinate right there. What is that coordinate? 0, 6. What is the slope at that spot? 0, right? Well, notice if you plug it in, we said y prime is equal to negative x over y. Well, if you plug in 0 for x and 6 for y, you get negative 0 over 6, which is 0. What's your slope here? Undefined. It's a vertical line, right? And this coordinate is 6, 0. Well, if we were to plug in 6, 0, we get negative 6 divided by 0, which is undefined. So this does tell us the slope at any point on the circle. The difference is instead of just plugging in x value, you also need to plug in a y value. Okay. Now, how did we come up with the derivative? What we did is we took the derivative of x squared, you got 2x. We took the derivative of 36, you got 0. But the one that's weird is when you take the derivative of y squared, you get a 2y, but you attach a y prime. Every time you take the derivative of a y, you attach a y prime. Are these the same or different? Same. They're lines, right? What's the slope of this line? 2. So the derivative should be 2, right? So let's take the derivative. Y prime is equal to, what's the derivative of 2x? 2. Now, here's what you really did. What's the derivative of y? It's 1 times y prime. Watch, you'll see it right here. What's the derivative of 5y? 5 times y prime equals derivative of 10x. 10 divided by 5, y prime is 2. See? The only reason why we haven't talked about it yet is because we've always seen just that the derivative of y is 1, and you just attach a y prime. So the important piece that we've learned is that anytime you take the derivative of a y, you must attach a y prime. So let's go to this sheet right here. We'll skip through that spot that we were talking about because we're a little bit behind for time. And we will use implicit differentiation to find the derivatives of the following equations. 3x squared minus 4y equals 4x. What's the derivative of 3x squared? 6x. What's the derivative of negative 4y? Negative 4, and you have to attach a y prime equals derivative of 4x, 4. Solve for y prime. Negative 4y prime is equal to 4 minus 6x. Divide by negative 4. Y prime is negative 1 plus 3 halves x. Not too bad, huh? Let's change it up a little bit. What's different about b? a couple of y's. What's the derivative of 3 or y to the third? 3y squared times y prime. Every time you take the derivative of a y, you attach a y prime. Minus 5 plus 2y prime equals 3. Now, you want to solve for y prime, and we actually talked about this last year, how you would do that in this case. If we want to solve for y prime, what we have to do is everything that has a y prime needs to be on one side, and everything that doesn't have a y prime needs to go on the other side. So I'll move the 5 over. I have a 3y squared y prime plus 2y prime is equal to 8. How can I isolate the y prime? Factor it out. Very good. Y prime times 3y squared plus 2 is equal to 8. Now what? Divide. So y prime is 8 over 3y squared plus 2. You remember that skill from last year we learned? Spent a very short time on it, but we did. We factored out and solved. Okay, you try C on your own. Go. I will slowly work behind you. You get 9x squared minus 1 over 4y minus 16y to the third. It is simplified. If you would put your y primes on the right side instead of the left side, you would get 1 minus 9x squared over 16y to the third minus 4y. Are those the same? Y. Yeah, top and bottom differ by a factor of -1. -1 over -1 is 1. Good. Okay. See? You can do it, can't you? Let's try problems that are slightly more difficult. D. What makes D more difficult? X, Y. What does that mean? We got a problem? Product rule, yes, thank you. Yay. Right? Because you got times. It's not that bad. It looks bad. It's not that bad. Let's start here. What's the derivative of 5y squared? That was easy. What's the derivative of 9x? 9. So now we just need the derivative of 3xy. And we're going to do the product rule. What's the derivative of 3x? 3 times y plus 3x times, what's the derivative of y? 1 y prime. Derivative of 3x, 3 times y plus 3x times the derivative of y prime. Just did the product rule. Now, gather the y primes on one side. So 3xy prime minus 10y prime equals -9 minus 3y. Okay, let's look at kind of the content limit, as I like to call it. You won't be asked a question more difficult than that. Let's look at x plus xy equals sine of xy. You can add that right on the bottom. So I think that E, from what I've seen, I would say is about the most challenging type of implicit differentiation problem that I've seen on the AP test, or one that I would ask you on a test. Okay, I'm trying to show you some hard problems, folks, so that we can over prepare you for our test. What's the derivative of x? 1. Derivative of xy, what do I have to do? Product rule. What's the derivative of x? Times y plus times equals. Ooh, now what? Yes! What's the inside? What's the outside? Sine of u. All right. And derivative of sine of u is cosine of u. Derivative of xy. We just took it. Yeah, it's right here, right? So I've got that thing, the whole thing, times the cosine of that. Right here. So that's equal to this guy. And I'm going to distribute through y cosine of xy plus xy prime cosine of xy. Got it, Hannah? Oh, no. That was my derivative. Okay. 1 plus y plus xy prime equals. Okay. I'm sorry. I'm not. Can you say your question? How did I get this part? So what I did is I distributed the cosine of xy through to each parts of that binomial because I have to be able to separate the y primes. So I have xy prime minus xy prime cosine of xy, and then I'll put my other stuff over there. Whoop. Factor out a y prime and divide. There you have it. I would say that that's a very good example. Both examples, D and E, are excellent examples of what you would see on the AP exam. I would say A, B, and C are too easy for what you would see on the AP exam. Every single thing I've seen on the AP exam for implicit involves the product rule at some point. We don't have time for our last problem. We'll have to do that at the beginning of class tomorrow. But the assignment, we do have time to put that on the board for you. Page 188, 5 through 12, and then 17, 19. You don't know how to do these last ones yet because we need to do that example tomorrow. But I think you should have some good success today. In my opinion, I've always felt that this test is one of the harder tests that we have over the course of the year. Now, last year they did very well with it. I think once you see the study guide, which I'll give you tomorrow, you'll feel much more confident about what you know and what you don't know. Again, I'm trying to over prepare you by showing you difficult derivative problems. So you're gonna have a lot of time to work on Wednesday if we stay focused tomorrow. No, I would have to run you copies of the note or papers. Yes. Otherwise, if you stop by my room by the end of the day, I could probably make some copies for you. Okay. I totally forgot today when I got the assignment.